Hello and welcome to all students. In this lecture, we learn about orthogonal trajectories. And in the previous lecture, we studied what is mean by exact differential equation and the solution of exact differential equation. And we solved some examples on exact differential equation also. Now, in this lecture, we learn about orthogonal trajectories. Suppose that we have a family of curves given by f of x comma y comma c equal to 0, one curve corresponding to each c in some range of values of the parameter c. In certain applications, it is found desirable to know what curves have the property of increasing a curve of the family 1 at right angles whenever they do intersects. That is, we wish to determine a family of curves with equations g of x comma y comma k equal to 0, second equation, such that at any intersection of a curve of family 2 with a curve of the family 1, the tangent to the two curves are perpendicular. The families 1 and 2 are then said to be orthogonal trajectories. Okay, so this is the definition of orthogonal trajectory. So are then said to be orthogonal trajectories of each other. If two curves are to be orthogonal, then at each point of intersection, the slope of the curves must be negative reciprocal of each other. That fact leads us to a method for finding orthogonal trajectories of a given family of curves. First, we find the differential equation of the given family, then replacing dy by dx by minus dx upon dy in the equation yields the differential equation of the orthogonal trajectories to the given curves. It remains only to solve the latter differential equation. So far, we have solved differential equations of only one form, mdx plus ndy equal to 0. The word orthogonal comes from the Greek upon, right, and yacht, angle. The word trajectory comes from the Latin trajectus, cut across. Hence, a curve that cuts across certain others at right angles is called an orthogonal trajectory of the others. For such an equation, dy by dx equal to minus m upon n. So the differential equation of the orthogonal trajectories is dy by dx is equal to n upon m and dx minus mdy equal to 0. Okay. So just solve these two differential equations. You will get the orthogonal trajectories of each other. Okay. So let us solve the example. Find the orthogonal trajectories of all parabolas with vertices at the origin and foci on the x-axis. The algebraic equation of such a parabola is y square is equal to 4ax. Hence, from y square upon x is equal to 4a, we find the differential equation of the family 3 to be 2x dy minus y dx equal to 0. So orthogonal trajectories. Therefore, the orthogonal trajectories of the family 3 must satisfy the equation 2x dx plus 2x dx plus y dy equal to 0. From phi, it follows that 2x square plus y square is equal to b square, where b is a arbitrary constant. Thus the orthogonal trajectories of 3 are a certain ellipse 6 with the centers at the origin, see in the figure. Okay, so orthogonal trajectories of given curve are the ellipses, okay, and given curves are the parabolas. So there are some examples given here. We can take a screenshot and try to solve the examples here. In each exercise, find the orthogonal trajectories of the given family of curve. Draw few representative curve of each family whenever a figure is requested. Now let us go to the next topic, additional topic on the differential equation of order 1. So finding an integrating factor by inspection. So finding an integrating factor by inspection. In section 11 we found that any linear equation of order 1 can be solved with the aid of an integrating factor. In section 19 there is some discussion of test for the determination of integrating factors. At present we are concerned with equations that are simple enough to enable us to find integrating factors by inspection. The ability to do this depends largely upon recognition of certain common exact differentials and upon the exercise. Below are four exact differentials that occurs frequently. So first differential is d of x y, means d of product x y, and its derivative is x dy plus y dx, so product rule. Now second differential is d of x upon y, and it is equal to y dx minus x dy upon y square. And third differential is d of y upon x, it is equal to x dy minus y dx, x dy minus y dx divided by x square. Now fourth is d of tan inverse of y by x is equal to x dy minus y dx divided by x square plus y square. Okay, note the homogeneity of the coefficients of dx and dy in each of the differential. A differential involving only one variable such that such as x square dx is an exact differential equation. A differential involving only one variable such as x square dx is an exact differential. Example first, let us try to solve the equation y dx plus x cube y square dy equal to 0. Let us group the terms of like degree, writing the equation in the form y dx plus x dy equal to x cube y square dy equal to 0. Now the combination, let us consider the differential equation y dx, fifth differential equation, y dx plus x cube y square dy equal to 0, and let us group the terms of like degree, writing the equations in the form y dx plus x dy plus x cube y square dy equal to 0. Now the combination y dx plus x dy attracts attention So we write the equation obtaining d by d of xy plus x cube y square dy equal to 0. Since the differential of xy is present in equation 6, any factor that is a function of the product xy will not disturb the integrability of that term, but the other term contains the differential dy and hence should contain a function of y alone. Therefore, let us divide by xy cube and write upon xy cube and plus dy upon y equal to 0. The equation above is integrable as it stands. A family of solution is defined by, just write the integration and we get minus 1 upon 2x square y square plus log y equal to log c. So log means log to the base e and thus we get finally 2 times x square y square log cy equal to 1. Example B, solve the equation y into bracket x cube minus y dx minus x into x cube plus y dy equal to 0. Now let us group the terms of equation 7 to obtain x cube into bracket y dx minus x dy minus y into y dx plus x dy equal to 0. Recalling that d by x upon y is equal to y dx minus x dy divided by y square. We divide the terms of equation 8 throughout by y square to get x cube into d by x upon y minus dxy upon y equal to 0. Equation 9 will be made exact by introducing a factor if it can be found to make the coefficient of d by x upon y a function of x upon y and the coefficient of d of xy a function of xy. Some skill is obtaining such factors can be developed with a little practice. There is a straightforward attack on equation 9 which has its good point. Assume that the integrating factor desired is x raised to k y raised to n, where k and n are some determined to be determined. Applying the factor we obtain equation number 10. Since the coefficient of d by x upon y, d of x upon y is to be function of ratio x upon y, the exponents of x and y, in that coefficient must be numerically equal but of opposite sign, that is k plus 3 is equal to minus n. In a similar manner, from the coefficients of d by xy, it follows that we must put k equal to n minus 1. From the equation 11 and 12, we conclude that k equal to minus 2 n equal to minus 1. The desired integrating factor is x raised to minus 2 y raised to minus 1 and 10 becomes x upon y d of x upon y minus d of xy upon x square y square equal to 0. Of which a set of solution is given by 1 upon 2 x upon y square plus 1 upon xy equal to c by 2. So finally the solution of the given differential equation is x cube plus 2y is equal to c into xy square. Now let us go to the example number C, and you see this example. You try to solve this example as your own. Take a screenshot Okay, so let us we stop here and we will see the remaining part in the next lecture.